All right, welcome back. I'm going to talk to this time about energy efficiency and something called the energy code. The energy code that we're going to use in this class, because most of the country uses the same energy code, is ASHRAE Standard 90.1. Now, ASHRAE Standard 90.1, its name is a standard. It's developed by a trade association, ASHRAE, the American Society of Heating, Refrigeration, and Air Conditioning Engineers. The exact same folks that came up with ASHRAE Standard 62, which is the ventilation standard, and ASHRAE Standard 55, which is the standard for filters. They also came up with an energy code. In other words, recommendations, it's a standard, recommendations for energy efficiency. However, after they developed this, and this has been years and years and years ago, it was such a good set of recommendations that most of the states in the country decided to use that as the basis of their energy code. And the International Code Council, the same ones that write the International Building Code, the IBC, the International Mechanical Code, the International Plumbing Code, they also write the International Energy Code, and it's based on the previous version of ASHRAE. In other words, they were like, yeah, we write codes for a living, and we're not going to write a better one, so let's just use theirs. So as part of this class, we're going to use one or two lectures to talk about energy and energy code. We're really going to talk about the energy code just in this lecture. And then the next time, next week, we're going to do an example that is an energy calculation. All right, so what I wanted you to understand is ASHRAE Standard 90.1 is the energy code. It changes every 3 years. They're on a 3-year update cycle. The one that I'm going to use for this class is 2007, which means it's quite a bit old. It's the older version than what we use today in the state of Iowa. However, if you learn on one, you'll be able to apply this to all the others. And they update fairly frequently, and there's no telling when the state will update to the newest one. Just because ASHRAE comes out with the newest version does not mean that anyone's going to use it. So just understand that. So we're going to take a look at the 2007 version. And I'm only going to give you a few pages of it. It's like this thick. It's a stack of papers this thick. I am not going to have you look at all of that. If you want to learn more about the energy code, I actually teach the current version in ConE 354. It's an elective class, and usually only mechanical emphasis students and mechanical engineers take it. If you're going into the HVAC world, it'd be a really good class to have, but otherwise might not see the utility of it. So we're going to talk about the 2007 version, knowing that it's old and outdated, but the same lessons apply to the newer versions. The first thing to understand is that what they've done is they've broken the United States up into parts. Oh, also, you have this handout. It's uploaded into Canvas, so if you don't have it printed out, you might want to print it out and take a look at it. We're going to need this, and then we're also going to need the Part 2 notes pack for this section of the class. So if you don't have those things, go ahead and pause, go get them, print them out. Might be handy to jot some notes down. All right, once again, this is an in-color drawing, and it doesn't look very good in black and white. The only point of this that I want you to realize is that they took the United States and broke it into zones. See, Zone 1, Zone 2, Zone 3, Zone 4. We're in Zone 5. It's hard to tell, actually, from this map, but we are in Zone 5. If we go out west, though, still Zones 1 through 5, but notice we're in the part of the country designated as moist. There's dry, and then there's marine right here along the edge of California. And which zone you're in and which type of climate you're in determines what the energy code is for the building components. Because the next part of this, and this is very important, is that what is the code minimum requirement for a wall or a window is determined by what part of the country that you're in and what zone that you're in. So a code minimum window in Florida is different than a code minimum window in Iowa and is different than a code minimum window in Southern California. Different climates require different things with regards to efficiency. All right, so let's continue on. Let's go to the next page. All right, so this is the table for U.S. climate zone that I printed out for Iowa. And most of Iowa is in zone 5A, except some of the northern tiers of counties. They're in zone 6A. But Ames, Des Moines, most of the parts of Iowa that you're going to be concerned with are in zone 5A. So then what I did is I printed out table 5.5-5. So this is for climate zone 5. So what this tells us is if I need to know what is the minimum energy performance level for a wall, a floor, going down, glazing, doors, skylights, I can look at this table and find out. Notice, it varies. We've already determined that it varies based on what part of the country that you're in. And then it also varies depending on, are we non-residential, are we residential, or are we semi-heated? Semi-heated. Think of a warehouse that is heated but it is not cooled. And it might not even be heated all the way to 72 degrees. But it does have some heat to it. All right, so residential, think like high-rise apartments. That's what this is really applying to. For this class and for the vast majority of the projects that you're going to be involved with, you need to look at the non-residential values here. Okay, so you can just go ahead and circle those. That's what I'll be asking you questions on. That's what you'll need for your final project. All right, next, let's just look at roofs. Okay, let's just start there. Let's have a look at the roofs, and I'm going to zoom in just a little bit so this shows up a little bit better on the screen. So depending on what type of structure that you have, right, whether this is insulation is entirely above deck, that's going to be most of them. If we're talking about a commercial or educational building that has a low sloped roof, and we have the structure, and then above that structure is the insulation, which is, like I said, the vast majority, you're probably going to be using this value. Now, notice, the assembly maximum is this number. The U value equals 0.048. But you have to have a minimum insulation R value of 20, and that insulation has to be continuous. See where it says CI? That's an R20 continuous insulation. It doesn't have any thermal short circuits that stick through it. All right, and that's going to be even more important when we look at walls. For roofs, this is probably not a big deal. We've just got R20 polyisocyanurate. You put it right down on top of whatever the structural deck is, and there you have it. Now, this is slightly better than this, and that's due to interior air films and that type of thing. But this is saying that you can't have any worse U value than this, and your R value has to be at least this R of 20, and then it has to be continuous. That's decent. I mean, it's not earth-shatteringly good, but it's pretty solid. All right, and that brings me to something that I want to point out. In the United States, during my career, we've taken a lot of good steps towards taking the energy code seriously. Let's just use Iowa as an example. Iowa used the 1989 version of the energy code up until about 2002. I had graduated from college. I was a practicing engineer in Des Moines, and they finally changed the code from the 89 version up to, I think at that time, we went to the 2001 code. The 1989 energy code was so bad that you would have had to have worked hard to violate it. It was so bad that in that day, most architects didn't even realize that the code applied to them for two reasons. One, in those days, nobody checked. There was never an inspection to make sure that you were code compliant for energy code. And it was so bad, you probably were, even by accident, you could probably get away with being better than the energy code. So then they went to the 2004 and then the 2007 fairly quickly, within the next 5 years after that. That was a huge change. Not because that these values were so earth-shatteringly good. It's just that, one, somebody was checking it all, and two, it was at least a decent value. Here, let's look at this. Let's look at the walls. For a mass wall, think precast concrete or brick and block. You have to have a U value of 0.09 and an R value for continuous insulation of 11.4. So continuous insulation, that's got to be between the brick and the block. Well, it doesn't have to be, but most of the time in a cavity wall, it's that insulation that is outside of the block but inside of the brick part of that wall. And that has to be an R value of 11.4. In all honesty, this also isn't all that awesome, but it is something at least. And they did start to inspect. Look at steel framed. Now, this one is interesting. A U value of 0.064. Now, what you'll notice is that if you add this R value of 13 plus an R value of 7.5 continuous, and then take the inverse of it, it does not equal 0.064. What they're saying here is that you've got to put an R value of 13 between the studs, and then an R value of 7.5 that is continuous across, that does not go in between the studs because of the thermal short circuit. You can get, if you put all of it continuous, you could easily exceed this, but they're acknowledging the fact that insulation between the studs is not going to give you this net R value. And they put it this way so that it's easy for a building inspector to inspect. So they can look at the face of that insulation that's between the studs and they can see if that's an R value of 13 or not. And then they can easily check to see if there's some rigid insulation that goes outside of the studs that's continuous at that 7.5. And they do the same thing here at in between wood studs as well. It's the same total performance level. It's just they acknowledge that wood plus this 3.8 is better than steel around 13 plus 7.5 continuous. In all honesty, these aren't exactly earth-shatteringly good values. But once again, it's a start, and at least they're inspecting. The other ones that are important, let's drop down here to the assembly U value for glazing. All right. Now, something important, you're not going to see it on this page, but elsewhere in the code, it says that the maximum amount of glass that you can have in a building is 40% glass. If you go above 40% glass, and many buildings do, you've got to do some other trade-offs in the building envelope to get its performance above the 40%. All right? So just understand there's ways to do that. There's exceptions, but they're kind of complicated, and you would have to do a whole building energy analysis to do that, and I will probably talk about that next week. All right, so let's check out some of the U values. All right, so metal framing, curtain wall, storefront, that's a lot of the windows that you're going to see in commercial buildings. Has a U value of 0.45 as a minimum. All right. And this SHGC, this is not like there is a conversion factor between this and a shading coefficient. I'll give you that conversion factor. I think it's in the notes in a little bit. Anyway, there's a conversion factor to change this to a shading coefficient. But these are pretty decent. A U value of 0.45, or if it's metal framing, all other 0.55. Those are at the very minimum. Those are dual pane glass windows as a start and some type of a thermally broken window frame. It's a good start. You can get a lot better, but that's decent. All right, now let's keep going. I am not going to go through all these values, but what I want you to realize is that for air conditioning systems, they're going to list efficiencies. Sometimes they're going to use terms like EER, energy efficiency ratio. We can't use efficiency for air conditioning as a percentage. If we're taking a furnace or a boiler and we're burning a certain quantity of natural gas, the percentage makes sense. But all of these energy efficiency ratios are different forms of kilowatts of electricity consumed per ton of cooling capacity generated. And that's the way I like to think of them. So in the handout notes, I converted this EER, this energy efficiency ratio, to kW per ton. This EER has to do with BTUs of energy transferred versus BTUs of energy consumed, and I'm just a fan of thinking all of it as kilowatts per ton. All right, now table 6.8.1. This is a good one to look at and to know. Gas-fired furnaces have a minimum efficiency, a thermal efficiency of 80%. And then there's a testing procedure on how you get that. 80% is going to be the code minimum on boilers and furnaces. So if I have a certain amount of heat energy input in natural gas and I set that on fire and put it through a furnace, 80% is how much of that energy went into the house. In other words, did something useful that I was wanting to pay for. And if I get 80% of that energy that I bought turned into useful energy in the building, then that's what our code minimum value is. And remember, we're talking about condensing boilers and condensing furnaces. Those start at 88% and higher. So this is that there's considerably better options than these code minimum values, and there's tons of chances to purchase different systems that are quite a bit better than 80% thermal efficiency. We're getting into the same thing for hot water boilers, for steam boilers. Notice steam boilers could be a little bit less efficient. By their nature, steam boilers are not near as efficient as hot water boilers, but just know that. Now we're getting into performance for, let's see here, cooling towers in terms of gallons per minute per horsepower. Once again, nothing to get terribly concerned with, but here, this is the next one. Not only does the energy code, the part that I'm most concerned that you learn is not so much what these individual values are, although I will test you on the individual building envelope values on the exam. What I'm really concerned with is that you know what is governed by the energy code and what is not. The building envelope, anything on the outside of the building that stops heat transfer, walls, windows, roof, that whole thing. All right, so building envelope. Mechanical equipment, anything that heats the space, anything that cools the space, any fans or pumps or anything that moves energy and air and water around the building. Those are all governed by ASHRAE standard 90.1. Lighting power, the electricity that we use to generate visible light. This is in a density of watts per square foot. Notice for, let's just take some common ones. Let's just look at offices and then classrooms. Offices have a watts per square foot of about 1. Classrooms, let's see here. If we look at schools and universities, 1.2 watts per square foot. Our current energy code is just a slight bit lower than this. You'll have to ask Jenny what it is if she gets into it. Like I said, this is the 2007 version, so it's just a little bit out of date. But something important to know, though, is that modern light fixtures, LED light fixtures, are capable of getting down to half of these levels, like around half a watt a square foot, 0.6 watts per square foot. They are much, much, much better than they ever used to be. So I just want you to know that it's governed and that this is the average here. This is the building area method. If you took the whole building area and you divide out the watts of electricity used on lighting per square foot of area, that's what this limitation shows us. All right, let's take a look at this next handout that I included in here. This next handout is really a good way of comparing energy sources. This was done, 10 years ago by the Iowa Energy Center. It's a little out to date, but being out to date, I think, is fairly interesting. So what it does is it compares, and this is really based on a residence. It compares different energy source fuels and different heating equipment and their efficiencies, and takes a look at the cost for a year in a residence of operation. And that's why I like this, because most owners, they're asking you, remember I said this last time, their question is, well, I want an efficient system. What they really mean is I want a cost-effective system. What is the cost-effective option that I have? In other words, what's going to be the cheapest to heat and cool? Now, let's look at the different options that they give us. Like, for example, natural gas at $1.71 per 100,000 BTUs. This is something important to write down that you're going to need for next week. 100,000 BTUs is also known as 1 therm of energy. When it is bought and when it is sold, natural gas is sold in therms. So keep that just something to note here. Same way with propane. Propane is usually sold by the gallon, but 1 gallon of propane is very, very, very close to a therm. And so we kind of use it as the same comparison. Some important things to look at here. 10 years ago, we were doing energy studies for natural gas at $1.71 per therm. Today, the cost of natural gas is somewhere between 50 cents and $1 per therm. It is half as much as it was then. And the reason for that, and we're going to talk about this as we talk about different energy options and different energy rates, the reason for that is the availability of natural gas. We have found more natural gas. We've been able to find natural gas deeper, and we've been able to harvest that natural gas through fracking. So that has caused natural gas price to go down by half of what it was 10 years ago, which is absolutely amazing. When I was doing energy studies 10 to 20 years ago, we were easily using this $1.70 per therm and wondering how much higher it was going to go. It's absolutely fascinating. So what happened is natural gas has gotten cheaper, and look at this electricity rate. The low electricity rate is 5 cents a kilowatt hour. The high electricity rate on this analysis is 10 cents a kilowatt hour. For a residence, this is probably too low. It's probably more like almost 10 cents a kilowatt hour for a cheap residential rate, and maybe more than that. Maybe like I'm on a rural co-op, so we pay like 15 cents a kilowatt hour. So this has actually gone up. Well, what has happened in the last 20 years? Natural gas has gotten cheaper because we found more, and electricity has gotten more expensive because of increased demand and the increased price of generation. We're going to talk a little bit more about the generation part next Monday, but the cost of generation, I want everyone to understand that today, right now, the cost to generate a kilowatt hour of electricity using solar energy or using wind energy is greater than the cost of generating that kilowatt hour of electricity by burning coal or even using nuclear power. However, from the standpoint of the power company, they can build a wind turbine and put it up and not get any heartache with regards to regulations, the neighbors, that sort of thing. If they go to put up a new coal-fired power plant, they'll get sued and sued and sued, and there'll be all sorts of environmental regulations and governmental regulations, and it just is almost to the point where it doesn't make much sense to put up any new systems. Even look at Iowa State. When they put up extra electrical generating capacity, they didn't use another coal-fired plant. They actually decommissioned one of their coal-fired boilers and put in 3 natural gas-fired turbines because natural gas has gotten so cheap. This didn't used to be the case. It used to be that turning on your natural gas turbines was actually more expensive. A more expensive way to generate electricity. So times have changed a little bit. Notice this other one down here. Shelled corn. Years and years ago, when corn was so dirt cheap, they were selling corn furnaces left and right across Iowa. Corn went up in price. People got rid of their shelled corn burners. Now corn's down in price. Now it's probably going back up in price. All of these, and this is an important thing to understand, all of our energy sources are commodities. They rise and fall in price with respect to availability and respect to demand. Availability can change demand, but so can other external factors like government regulation and public opinion. So let's take a look at each one of these. Natural gas at $1.71 a therm, a 92% efficient furnace, it'll cost you $18.59 per million BTU. That is million BTU in the house, in the living space. Here, notice this. Net cost delivered to the living space. The 75% efficient furnace is obviously going to cost you more. $22.80 per million BTU delivered. Propane, all right? Propane, probably more likely to use if you're in a rural setting where you're out in the country and you don't have piped natural gas. Probably a little more expensive. Not this expensive today. If this is down around 75 cents, this is probably $1, $1.10. Quite a bit cheaper, but still more expensive than natural gas. Fuel oil, rarely used here in Iowa, and I'm not gonna talk about it because of that. I want to get into the electricity. All right, electricity, 10 cents a kilowatt hour, 5 cents a kilowatt hour. Here, if we look at this, one coefficient of performance resistance electric heater. A coefficient of performance of 1. This is another term kind of like EER. Coefficient of performance of 1 means for every kilowatt of electricity I consume, I transfer 1 kilowatt of electricity into our living space. I said, wait a minute, that's 100% efficient. No, not quite. It's ignoring all of the losses upstream of that plug-in. In other words, the losses in energy to take coal and burn it in a turbine, to transmit that electricity across the grid and into your house, those are all ignored. This only takes into account electricity consumed at the outlet versus heat put into the house. And for an electric resistance heater, all of the heat is turned into friction, and all of that friction is dissipated by the air within the room itself. So the coefficient of performance for a resistance heater is 1. 1 kilowatt of electricity consumed, 1 kilowatt of heat put into the room. All right, let's take a look at the geothermal heat pump, though. This has a coefficient of performance of 3.6. 3.6, meaning I get 3.6 kilowatts of electricity transferred. 3.6 kilowatts of heat transferred in the refrigeration cycle versus 1 kilowatt of electricity consumed by the heat pump itself. And something to be cautious of here. This is not like saying this is 360% efficient. It's not generating electricity magically. But what it is doing, it is transferring more heat from the ground than it is consuming in electricity. And I hope everybody understands that particular concept. Let's go back to the heat transfer in a refrigeration cycle. Remember, it has to reject more heat out of the system than it consumes, because all of that is being translated into friction, and all of it gets rejected somewhere. In a ground source heat pump, it's taking some energy out of the ground, it's consuming some energy in the compressor, and all of that is rejected at the condenser. And in a heat pump, that condenser is inside, so all of that heat goes to heat the house. Notice at 10 cents a kilowatt hour, that heat pump with a coefficient of performance of 3.6 is way cheaper than any of our other options. Well, except for when we go down to the even cheaper electricity rate. At an electricity rate of 5 cents a kilowatt hour, obviously it's even less. These rates were true 10 years ago. They are not true today. So something to keep in mind is that if you made the decision of which of these systems to purchase for your house, and you picked the heat pump, it was a whole lot cheaper then. It may not be that much cheaper today to run. And here's the thing, is that in terms of first cost, and this is the example we're going to work next week, what if this heat pump cost you a lot more to install first cost than that gas-fired furnace, which it did? You might be counting on that cheap electricity to help pay for the first cost of the equipment, and maybe that hasn't necessarily materialized, because here 10 years later, the energy rates are very, very, very different. All right, so let's go back to the lecture notes, page 68. So what the energy code does is that it allows us to set some minimum energy levels of performance, but what it also does is that it allows the designers, which are not in that particular table, but it's in the energy code, it allows the designers to make trade-offs between code minimum equipment for improved energy efficiency in some areas versus reduced energy efficiency in the other areas. That's a more complicated topic that's discussed in Connie 354. I just want you to know that it is allowed, so that when you see a building and you're like, wait a minute, why is that building a whole lot more than 40% glass? What they've had to do is they've had to offset that reduced performance for all the extra glass with energy efficiency improvements somewhere else. Usually the trade-off that designers make is they trade energy efficiency in the building shell for improvements in energy efficiency elsewhere. Usually it's a more efficient chiller and boiler or other mechanical equipment. It's also a more energy efficient more energy efficient lighting system. So lower kilowatts per square foot of floor area for the lights. All right. So here's that efficiency of the refrigeration cycle. Remember, on the heat pump, this Q out at the condenser is actually being rejected into the house. We are rejecting our heat. The energy that we pulled in from the ground plus the energy at the compressor all goes out at the condenser, which is in the room for a heat pump system that's running in heating mode. So a coefficient of performance is very different than an energy efficiency, just like a thermal efficiency as a percentage. Be cautious here. I have heard heat pump salesmen say something like, heat pumps are always better than gas-fired furnaces and boilers because the best you can get a furnace is maybe 96% efficient, whereas a heat pump is 300% efficient. Don't fall for that. That is not comparing accurate energy efficiency terminology to one another. The best way to compare one system to another is like this other page, is in dollars. That is the best way to compare efficiency, and that is dollars consumed per million BTU of usable space in the or usable heat within the space. And that's the way an owner is going to be able to understand it best themselves. But I want to explain these coefficients. Always look at, when we're talking about refrigeration cycles, I really always like to think of it of kilowatts per ton. EER is just take 12 divided by EER, that gives you kW per ton. Right? Coefficient of performance, if you take 3.513 divided by the coefficient of performance, that also gives you kilowatts per ton. The best way to think about air conditioning systems is kilowatts of electricity consumed versus ton of cooling capacity. All right. For coefficient of performance for heating, remember, it's always got to be 1 or greater than 1. Okay? The greater the coefficient of performance, the better that it is. All right. Let's see here. Some examples here. So I broke this down for you to give you some examples of some different types of cooling equipment and what their kind of some standard kilowatts per ton are. Like this first one is a kW per ton of 1.09. Think of this as like a really good residential split system with that condenser outside. That might be 1.09 kW per ton. For a ground source heat pump, though, you might be able to get that down to 0.9 kW per ton. A little bit better. Pretty good. An air-cooled chiller, probably down around 1.25 kilowatts per ton. Not as good as some of the other options. Look at this for the water-cooled chiller. You can get those at 0.58 kW per ton, and probably even better, some chillers are at 0.4 kW per ton and maybe even less. Like that magnetic bearing chiller is probably less than 0.4 kW per ton. Those are pretty awesome. For furnaces, right? 80% and better. Realistically, 90 to 96% is pretty good. Won't ever get to 100% thermal efficiency on a gas-fired appliance that has a heat exchanger. Just can't get there. All right. Let's see here. All right. Utility companies and demand charges. All right. So I'm going to pause there. And next week, we're going to talk a little bit about utility rates. And then we're going to go through an example of an energy cost calculation. So stand by for that, and that will be next week.